Start working through some different probability examples. Hopefully you've kind of have your formulas next to you and you're getting comfortable using those. So this first one, we've got a word problem, and they give us several different pieces of information. The first part wants us to take those 3 bullet points and convert each one into a probability statement. Even gives us some helpful information about some shorthand to use, F for female, S for speeding. So the first one, 18% of drivers are female on this particular stretch of highway here. So probability female is 0.18. And then the next bit, 89% are speeding. So probability of speeding is 0.89. And then I want you to take a moment and try and convert that last bullet point into probability notation. All right, hopefully you notice this phrase, of those speeding. So that's telling us we're not looking at all drivers, just the drivers that are speeding. So that's our given notation. So given someone is speeding, the probability of them being female is 0.15. So we've translated our 3 bullet points, or the given information, into probability notation. Now it should come in very handy for answering the remaining questions. Again, before I go through each of these in the video, I would suggest pausing it and trying it on your own to make sure you understand it, then watch and double check your work. So part B, find the probability a driver on this stretch of highway is female and speeding. So our notation to write that question in probability notation, probability female and speeding. Now remember our trick, we don't know if female and speeding are independent or dependent, so we need to use the general multiplication rule. So let's check out probability of female times probability of speeding. And then since we don't know if they're independent, we're not done yet. We have to go back and put a given in one of these terms. So up above, I know this, female given speeding, so that's the one I'll add the given onto, female given speeding. Now we're ready to go. We can plug in our values. The first is 0.15 from up above. The second, speeding, that's 89% of drivers from up above. And that gives us 0.1335. So if you tried this on your own and you just did F times S, make a big note to yourself, you can't do that because you don't know if they're independent or not. Next bit, given a driver on the stretch of highway is female, what's the probability they're speeding? So first, translate again, and hopefully you noticed our key word here, given. So our given information is that we're talking about female drivers. So that's going to go after the line. And then what we want to find the probability of out of those female drivers, or that given group, is a chance of speeding. So remember our formula here, write these every time so you start getting them stuck in your head. Speeding and female, it's the probability of both, over, and then remember which one goes in the denominator. It's always the given information, F, female in this case. Again, we have all this information, we're ready to go. So speeding and female is the same thing as female and speeding, doesn't matter the order. We found that number previously. We've got it labeled nicely, so we're not going to get confused there. And then our denominator, we need probability of female, which we had up above, was 0.18. And if we work that out, we're going to get 0.7417. All right, next bit. For the stretch of highway, are female and exceeding the speed limit independent or dependent events? So remember, independent is when the two sides of one of our 3 equations are equal. Dependent is when they are not equal. So choose any one of the 3. Doesn't matter to me. I'm going to choose one that requires the least amount of work. Female given speeding. So first write down what we're checking here. Female given speeding. And if they're independent, I want to see if that guy is equal to probability of female. Remember, our rule says the probability is female, the same with and without the given information. It's independent of it, makes no difference. So female given speeding, we saw up above, was 0.15. Also up above, we have the probability of female is 0.18. These are clearly not equal to each other. So when the left and right sides are not equal, it means they're not independent, or in other words, they're dependent events. If you wanted to test this using probability of female and speeding, that 0.1335, and see if it's equal to female times speeding, you're welcome to do that too, and you should come to the same conclusion. Finally, for this problem, are female and speeding mutually exclusive? So we mean mutually exclusive. We need to double check if the and is equal to 0 or not. Can they happen at the same time? So again, mutually exclusive means disjoint. So female and speeding, I want to see, is that equal to 0? Is there no way I can have a female who's speeding driving on this roadway? So probability of female and speeding, we found that earlier, was our 0.1335. Of course, there's females who are speeding while they drive. That may have been some of us before. Not admitting to anything here. But female and speeding, sure, there's overlap that can happen. So they're not disjoint or not mutually exclusive. All right, let's try a few other examples. The next one gives a whole lot of information. They tell us 71% have debt, so I'm going to jot all this down here. Probability of debt is 0.71. We've seen a lot of this. 16% go to private nonprofit, so probability private nonprofit is 16%. Of those who attend private nonprofit, so I'm not looking at everybody, I'm looking at a smaller group or a given group. So given the private nonprofit group, 75% have debt, so probability of debt in that group is 0.75. 73 attend public universities. There's a lot of information on here, drawing from other problems. We're going to have to think carefully about which pieces we need because of this information overload. 48 have both debt and attended a public university. So probability of debt and public was our 0.48. All right, so part A, what's the probability a randomly selected person attends a public university or has student loan debt? So probability of public or student loan debt. So we need to start getting good at converting the question into our probability notation. So probability of public or debt, remember our formula, add the two together. And then we don't want to double count that overlap, so we need to subtract the probability of both of those happening. So public universities, 0.73. And just a reminder, I'm not putting P notation around the numbers. Once I write the numbers down, those are the probabilities. I'm not finding probabilities of the numbers. Just leave them plain like that. Being in debt, that was 71% of people. And then those that have both debt and attend public universities, that was our 48% over here. And putting all that together, we're going to get nearly all students, 0.96, are either attending a public school or have debt. Next bit is saying are having student loan debt and attending a private nonprofit independent. Explain with probabilities. So I'm interested in debt and our private nonprofit. So let's see what kind of information we have. You might want to try the debt and private nonprofit. Is it equal to debt times private nonprofit? We can't really do that approach here because we don't know what the intersection is equal to. So we're going to have to use this conditional rule. So probability of debt given private nonprofit. I want to see, is that equal to the probability of debt? Remember, it's the same with and without the given information. So given the private nonprofit group, we know that 75% of them have debt. And that's definitely not equal to debt for among college students in general, which is a little bit lower at 71%. So since the left and the right-hand sides are not equal, these guys are not independent. Again, make sure you're showing all this information, what you're testing, the numbers you're plugging in, and your conclusion. Make sure you avoid things like just saying they are not equal. Show me what the they represents. All right, next one is going to be quite different from some of the other ones we've seen. So for this one, it says what's the probability the length was less than 10 feet and more than 5 feet? We've got this data on the length of harvest skins from nuisance alligators in Louisiana, just to judge the size of those. So we do have an and here, so I'm going to use that notation. I want probability, I'm going to say 10 minus for less than 10 feet. Feel free to come up with your own notation. And 5 plus for more than 5 feet. So we don't want to use any and formula here. This is a data and a table, though it's a different kind of table. Since these are disjoint, an alligator can't be both 5 feet and 6 feet at the same time. We can just add up probabilities. So this is strictly less than and strictly more than. So less than 10 feet would be these, and more than 5. This section is the overlap or satisfies both of those criteria, less than 10 and more than 5. So if we add those up, we're going to get 0.644. Again, just adding up the ones that represent the overlap or both of these things, less than 10 and more than 5. Our next part here is given the length was less than 10, so given, you're thinking, all right, I need that vertical line. The given information is less than 10. That goes after the line. So put that information here, less than 10. I want to find the probability of more than 5. So what's the probability of 5 plus given I'm only looking at ones that are less than 10 feet? So our formula, probability of both of these guys happening, 5 plus and 10 minus, divided by our given info, 10 minus. So the numerator we just found in part A. There's our 0.644. Our denominator, 10 minus, would represent this. All of these lengths that are strictly less than 10 feet. So if you add all of these probabilities up, that's my given group. I've got, that should give you 0.934. And you'll get 0.6895 here. So checking out those that are between 9 and 6 relative to just all those that are strictly less than 10. So we use the same formula, but it just looked a little bit different in this example. We'll have one final video with a couple more examples to get some practice.